Hi everyone. For this video we're going to be taking a look at a few theorems regarding arcs and chords. So let's jump right in. First, a little bit of review here. We need to remember that a chord is a segment whose endpoints lie on a circle. So if we look over here at circle A, segment BC would be considered a chord because its endpoints B and C are both on the circle. Now, in that diagram, segment BC kind of cuts off two chords from circle A. It kind of divides circle A into two chords. We have chord BC right here, and we have chord BDC. So those are the two chords that, the two arcs. I think I was saying chord there. I should have been saying arcs. Those are the two arcs that chord BC kind of cuts circle A into. Now the minor arc, BC, remember minor arcs are less than half of a circle, BC would be referred to as the arc of chord BC. So chord BC and arc BC, they kind of go together in a way. Chord BC created minor arc BC. And you'll need to remember that because for the next few theorems, they'll all be using this idea of a chord creating a minor arc in a circle. So in theorem 9-4, it says, in the same circle or in congruent circle, congruent arcs have congruent chords, and vice versa. Congruent chords have congruent arcs. So if I drew in, let's say I drew in chord BD. So let me quickly kind of sketch in chord BD. It's not going to be the straightest chord in the world, but you get the idea. If chord BD was congruent to chord BC, then that would mean that arc BD would be congruent to arc BC, and vice versa. If the arcs were congruent, then these chords that created them would be congruent. So that's all theorem 9-4 says. Next up, we got another little definition. It's a word that we've used before, but not in this context. If a point divides an arc into two congruent arcs. So if I look at this diagram right here, and let's say that point T divided arc SQ into congruent arcs ST and TQ, then that point T would be called the midpoint of the arc. So T could be referred to as the midpoint of arc SQ. And then any line or ray or segment that contained point T would be called a bisector of arc SQ. And so we've used these terms midpoint and bisector before, just not in terms of arcs. So to kind of illustrate that last part there, if I drew the radius from P out to T, so in other words, if I connected P to T like this, and you can see since T is the midpoint, then this segment contains the midpoint of arc SQ. That would mean that segment PT is a bisector of arc SQ. And that's all this little paragraph is saying there. So that brings us, though, to theorem 9-5, and in a way also theorem 9-6. Theorem 9-5 says that a diameter that is perpendicular to a chord, so in other words, we have diameter HI over here in circle E. If diameter HI was perpendicular to chord GF, that would be the situation we're describing here, then it bisects the chord and the arc. So in other words, if segment HI is perpendicular to chord GF, then first of all, it would bisect the chord GF. So GJ would be congruent to GF. GJ congruent to JF. I think I might have said GF just a second ago. I meant JF. And secondly, it also bisects chord GF. So arc GI would be congruent to arc IF. Arc GI would be congruent to arc IF. So that's what theorem 9-5 says. However, we can also remember that a radius is part of a diameter. So we could also apply this to a radius. If a radius is perpendicular to a chord, then that radius would bisect the chord and the arc. And the last theorem we're going to take a look at in this section is theorem 9-6, and it says, in the same circle or in congruent circles, all chords that are equidistant from the center or the centers, if we're talking about congruent circles, are going to be congruent. And secondly, congruent chords will be equidistant from the center of the circle. So, and remember, we measure the distance between a point and a line or a point and a segment. We measure that distance. So if we wanted to measure the distance from the chord BC to the center A, we have to measure along something that's perpendicular to the chord, right? We measure distances from points to lines or segments. We measure those distances along segments that are perpendicular to the object that we're looking at, right? So what this theorem would say, so part one of this theorem would say that if BC was the same distance away from A as DE, or in other words, if AG was congruent to AF, right? If this was congruent to that, that would indicate that this chord is the same distance away from A as this chord, DE. Then those chords, BC, would be congruent to DE. And it would also mean, just so we understand, if those chords are congruent based on what we learned earlier, it would also mean that arc BC would be congruent to arc DE. If we applied theorem 9-4 to what we just said here about theorem 9-6. The second part of theorem 9-6 was just like the converse of the first part. So in other words, if we knew that BC was congruent to DE, if those chords were congruent, then their distances away from the center would be the same, meaning that AG would be the same as AF. Oops. Let's write that as AF. All right? So that's what theorem 9-6 tells us. So, with that being said, I want you guys to try the examples there's 4 examples that I want you to try. The video is going to pause here in a second, and I want you to try those. And then once you enter your answers, you can let the video play, and I'll explain what the answers would be. Okay? So good luck on those. All right, let's take a look at the answers. First, let's start with questions 1 and 2. Let me get those on the screen there. So in question 1, we have this situation here. It looks a little confusing at first, but what you need to recognize is that we have diameter EF that is perpendicular to chord CB. So based on theorem 9-5, we would know that this chord has been bisected by this diameter, because a diameter that's perpendicular to a chord will bisect it. So that's where I said that since by segment addition, the length of CB would be equal to CD plus DB, and since CD and DB will be the same, and that's because of theorem 9-, that's because of 9-5, those would be the same, then it would tell us that CB would be equal to 15 plus 15, which is 30. So segment CB has a length of 30. It also wanted us to find segment AD. Well, we would recognize if this is a right angle, then so is this. So it's just a Pythagorean theorem problem. AD squared plus DB squared would be equal to AB squared. So I plugged in the values for DB and AB, worked out the Pythagorean theorem, and I got a length of 8 for AD. All right. Now in question number 2, we have a similar kind of picture here. It's actually pretty similar if you start comparing. And we have to find the measure of arc BDC and angle BAD. Well, first of all, we're given that this is 220 over here, and the full circle would of course be 360. So if I just take the 360 minus the 220, that will tell me that arc BDC has a measure of 140. And then, again, based off of theorem 9-5, we know that since this radius is perpendicular to this chord, It's going to bisect not only the chord, but it's also going to bisect the arc that the chord BC cuts off from the circle. So that would mean that the measure of BD would equal the measure of DC. And by arc addition, we know that BD plus DC would equal the measure of BDC, which we've already determined is 140. So that would mean that arc BD is equal to half of 140, which is 70. So we know that's 70 degrees right there. And if that's 70 degrees, then the measure of angle BAD would be equal to the arc BD's measure. So the angle BAD, because it's a central angle, this is back from section 3, that central angle would have a measure of 70 degrees. So that's 1 and 2. Let's take a look at 3 and 4. In number 3, we had, first of all, you might need to notice that in number 3, I actually had a typo on your note sheet. I fixed it for the video, but I think your note sheet said CD right there, and it should have been BD. So you might have had a little bit of a hard time figuring that out if you didn't notice that should have been BD. So anyway, since segment AF is congruent to segment AG, it would be indicating that chord CE is the same distance away from the center as chord BD. These segments would indicate the distance that these chords are away from the center. And since those distances are equal, it would mean that the chords are congruent, or the chords have the same length. And if the chords have the same length, then the arcs here, EC and BD, would be of equal measure. And since arc EC is 80, it would mean that arc BD would be 80. Lastly, in number 4, you had to draw a quick picture, so I went ahead and used a drawing program to do my picture because it would have looked really bad if I tried to draw it freehand. So we have circle O that has a radius of 12, and we have chord RS that is 6 centimeters away from O. So this little segment right here is indicating the distance that chord RS is away from the center O. So that's a 6. And since we're measuring the distance from the chord to the center, that segment would be perpendicular to the center. It would be perpendicular to the chord. And since that is perpendicular to the chord, it would mean that it would bisect the chord. So these two parts would be equal. And so by segment addition, RS would be equal to RM plus MS. The length of RS would be the length of RM plus the length of MS. But since the length of RM is the same as the length of MS, the length of RS would just be 2 times the length of MS. And we can find the length of MS by using the Pythagorean theorem, because we notice we have a right triangle right here. Some of you might have not realized that you could have drawn a radius right here from O out to where S is, or you could have done it from O out to R and accomplished the same thing. But if I drew in this radius that's 12 units long, that creates this right triangle, and I know 2 of the side lengths of the right triangle. So I can use the Pythagorean theorem right here to find this length right that I want, the length of MS, which is what I was trying to find. So I set up the Pythagorean theorem, I solve for MS, and I get the square root of 108, which simplifies to 6 root 3. Oh, but I didn't finish this problem. I just realized I forgot to finish this problem because I only found the length of MS. So real quickly here, if the length of MS is 6 root 3 or 10.4, then the length of RS would be 2 times that, which is 2 times 6 root 3, which is 12 root 3. Or if you're going to go a decimal, it'd be 2 times 10.4, which is going to be 20.8. So sorry about that. I forgot to actually finish that because it was asking for RS. So there you have it. That's section 4, 3 important theorems about arcs and chords. So we will see you in the next video.